Hi everybody. So in this video, I'm going to show you how to find the size and the power of a hypothesis test. We'll look at a normal, a Poisson, and a binomial distribution. And then we'll try an exam style question. If you want to work along with me, you can download a copy of this PDF from my website. I'll leave a link below. So in our first example, we're looking at a normal distribution where we're testing the average mu, and we're told that the variance is 4 squared. We've got a random sample of 30 observations, and we're testing the sample mean. So we're testing the null hypothesis that the mean is 25 against the alternative hypothesis that the mean is greater than that. And we're using a 5% level of significance. The first thing we need to do is to find the critical region. So if we assume then that the sample mean is distributed with a mean of 25, and a variance of 4 squared divided by the sample size of 30, then we can sketch this distribution, and we know the peak will be at the average of 25. And because our alternative hypothesis is that mu is greater than 25, it's a one-tailed test where we're looking at the region to the right. And this will have an area of significance level, which is the 5%. So this will have an area of 0.05. And we're trying to find this critical value here, which I'll label C. So the probability of the sample mean being greater than C has to be less than the 0.05, okay? And we can work out this critical value using our calculator. If we go to Home and we choose Distribution, we want normal, inverse normal. The area is going to be 0.95. That's the 100% take away the significance level. The average is 25, and the standard deviation is the square root of 4 squared divided by the sample size. And then we can execute that. So this tells us that the critical region is when the sample mean is greater than 26.2. Okay? This is when we reject HO and accept the alternative hypothesis. So then for part B, given that mu is actually 25.8, find the power of this test. Well, the power of a test is when we reject HO given that HO is false. So we can write this as the power we reject HO, that's we reject the null hypothesis given that the null hypothesis is actually false. And we've found the critical region where we reject HO. So a power will be the probability of x bar being greater than 26.2, given that mu is actually 25.8. And we can work this out on our calculators. If we go to normal CD, we want the lower to be 26.2, the upper to be 3 standard deviations or more above the mean, and the mean we're now told is 25.8. And the standard deviation is the same. So if we execute that, we get the power of the test to be 0.2919. Okay? So what that tells you is there's just over a 29% chance that if the average is 25.8, that we will reject the null hypothesis. And in the next question, we're going to look at a binomial distribution. So in example 2, we're given that the random variable y has a binomial distribution of 20 trials and a probability of success 0.25. And we're testing against the alternative hypothesis that p is greater than 0.25, again at a 5% level of significance. For part A, we need to calculate the size of the test, And then for part B, we need to calculate the power given the different value of P. So if we say our distribution, we assume that X is distributed binomially with 20 trials and a probability of 0.25. And I'll sketch this distribution. We know the expected value will be at n times P, so this will be at 4. And because we're testing that P is greater than a quarter, we're looking at the tail to the right. And this will have an area of that significance level, 0.05. So we need to find this critical value. So when we look at the size of a test, this is when we reject HO given that HO is true. So in order to reject HO, we need to find the critical region, which means we need to find this critical value. So if we say that the probability of X being greater than or equal to the critical value must be less than our significance level, then we can work out this critical value using our tables. So we know that P is the 0.25 and N is 20. So we're looking at the first probability that goes above the 95%. And it will be when X is less than or equal to 8. And this will have a probability of 0.9591. So if we go back to our notes, so we know that the probability of X being less than or equal to 8 from our tables is 0.9591. So we're looking at the critical region when X is greater than or equal to 9, which is 1 minus the 0.9591, which works out as 0.0409. So if we label on our diagram, now the critical value is, and this actually has an area of 4.09%. Then the size of a test is when we reject HO, so we must be in this region, given that HO is true, then this is a valid model. So you can see that the actual size of this test is the 4.09%. It's the area of this critical region. So we'll say the size is equal to 0.0409. And then to work out the power, and this is when we reject HO, so we're in this critical region, given that HO is false, and we're told that the probability is actually 0.28. So we'll say we reject HO given that HO is actually false. So a power will be the probability of being inside our critical region, so X is greater than or equal to 9, given that P is 0.28. And we can work out this probability as 1 minus X being less than or equal to 8, given our new value of P. So if we go back to our calculators, now we want binomial CD, so we'll go back. We want variable, we'll choose X to be 8, N to be 20, and P is 0.28. And we'll execute that, and we get 1 minus 0.9216. So if we go home, and we'll have 1 minus the answer, and we'll get the power as 0.0784. So 7.84%. So this means there's a probability of 7.84% that we would reject HO when P is actually 0.28. Okay? Let's have a look at a Poisson distribution. So now we're given the random variable X as a Poisson distribution. We're testing the null hypothesis that lambda is 3.6. Against the alternative, that lambda is less than 3.6. We need to find the size and we need to find the power given this new value of lambda. So perhaps you want to give this question a go yourself. You can pause the video and come back when you're ready. Okay, so welcome back if you had a go. If we assume that this value of lambda is true, we can say that x is distributed with a Poisson of lambda 3.6. And then I'll sketch its distribution. We know the peak will be at the expected value. And because lambda is less than 3.6, we're looking at the tail to the left. And again, this will have an area of the 0.05. And we want to find the critical value. So again, to find the size of the test, we need to be able to reject HO. So we need to find this critical region. So we're looking at the probability of x being less than or equal to c to be less than our significance level. And to work out this critical value, I'm going to use my calculator. So if we go to home, we want distribution, we want Poisson CD, we'll choose list, and we'll enter 0, 1, 2, and I want the first value of x which goes above the 0.05. So we'll execute that, we'll enter lambda as 3.6, and you can see that the first probability to go above the 5% is when x is 1. So when x is 0 is our critical region. We get the probability of x equaling 0 as 0.0273. If I include this on the diagram, we'll change the critical value to 0, and this will have an area of 0.0273. So this is the size of a test. This is when we reject HO, given that HO is true. So the size of a test is 0.0273. So this tells us there's a 2.73% chance of us rejecting HO, given that HO is true. And then for the power of a test, this is when we reject HO, given that HO is false. So we want the probability of x equaling 0, given that lambda is actually 3.1. And we can work this out on our calculators. If we go back, this time we can choose Poisson PD, because we want x to be exactly 0. And lambda is 3.1. We'll execute that, and we get the power as 0.0450 to 4 decimal places. Okay? So there's a 4.5% chance of us rejecting HO, given that HO is actually false. Let's try the exam style question. So in example 4, we're given this real life situation. Do you want to read through the question and then try and work out the size and the power given the correct value of lambda? You can pause the video, and when you come back, we'll go through the solution. Okay, how did you get on with that? And did you identify this as a two-tailed test? Well, let's go through it. If we assume that x is distributed with a Poisson of lambda 8, and then if we sketch this model, we know the expected value will be at 8. And because we're testing that lambda is not equal to 8, it's a two-tailed test, where each tail will have an area half of a significance level, so with 5%. We need to work out each of these critical regions. We'll call this one C1 and C2. And then the area of each critical region, so x being less than or equal to C1, and x being greater than or equal to C2 must both be less than that 5%. And we can work out these critical values from the tables. If we begin with C1, we'll go from 8, and we want the first one to go above the 5%, which is this one, when x is 4. So our critical region will be when x is less than or equal to 3. So we want the probability of x being less than or equal to 3. And this was given as 0.0424. Then to work out C2, we want the probability that is nearest to 95%, and that is the 0.9362, when x is less than or equal to 12. So we'll go back to our notebook. Probability of x being less than or equal to 12 was 0.9362. So this tells us that the critical region is when x is greater than or equal to 13, which is 1 minus that probability. We can work this out and we get 0.0638. So I'll identify each of these critical regions on the diagram. We've got C1 is 3, and this gives us an area of 0.0424. And then we've got C2 is 13, and this has an area of 0.0638. So then for part A, to determine the size of a test, we must be in either of these critical regions. So the size will be the probability of x being less than or equal to 3, or the probability of x being greater than or equal to 13. So we'll add the 0.0424 and the 0.0638, and we get the size of the test as 0.1062. Okay? And then for part B, the probability of a type 2 error, this is when we accept HO, given that HO is false, and for us to accept HO, we must be outside of the critical regions. So we want the probability of x being less than or equal to 12, but greater than or equal to 4, given that lambda is actually 10. Well, we can work this out as x being less than or equal to 12 minus x being less than or equal to 3. Again, given that lambda equals 10. So if we go to our calculators, we'll choose Poisson CD. This time I'll choose list. I want probability when x is less than or equal to 3 and 12. I'll delete that one. And lambda is actually 10. So we get 0.7915 minus the 0.0103. We can work this out and we get 0.7812. This is the probability of a type 2 error. And then finally, for the power of a test, this is when we reject HO, given that HO is false. Well, if this is when we accept HO, when HO is false, the probability of us rejecting will be 1 minus the 0.7812. We can work this out, and we get 0.2188. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe. And you can download the full lesson and a PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link below.